A boost regulator is a DC-DC converter whose output voltage is always greater than the input voltage. It uses a switching element to regulate steady DC output of required voltage. I am Reshma, and today we will discuss the operation of a boost regulator in continuous mode of operation. Today we will learn about inductor average current, inductor ripple current, inductor peak current in a boost converter in continuous conduction mode. Let us look at the inductor average current. Let us turn on the switch from time 0 to t1. At this time, the inductor current rises from I1 to I2. Now, the slope of the current is given as I2 minus I1 divided by t1 minus 0. Let us turn off the switch from time t1 to t. At this time, let the inductor current fall from I2 to I1. Now, the slope of the current is given as I1 minus I2 divided by t minus t1. We know the equation of a straight line with initial and final values. For the time period 0 to t1, the coordinates of the current are y2 x2 is equal to I2 t1, y1 x1 is equal to I1 0. This means y2 is equal to I2, y1 is equal to I1, x2 is equal to t1, x1 is equal to 0, x is equal to t, and y is equal to IL1 of t. Then, for on time, inductor current can be written as I2 minus I1 divided by t1 into t plus I1. For the time period t1 to t, the coordinates of the inductor current are given as y2 x2 is equal to I1t and y1 x1 is equal to I2 t1. This means y2 is equal to I1, y1 is equal to I2, x1 is equal to t1, x2 is equal to t, x is equal to t, and y is equal to IL2 of t. With this, we can write the falling current of the inductor as shown here. Let us group all the constants and with one with variables together. We get this equation. Let us simplify it. Now we get this as our falling current. With the equations we saw in the previous slide, we can write the total inductor current as IL1 of t for time 0 to t1, IL2 of t for time t1 to t. The average current is given as 1 by t into integral of IL of t into dt. On substituting the values for on and off times, we get the equation as shown here. Observe the obtained equations once again. These are similar to that of a buck regulator equation we saw in our previous video. If we solve this like we did in the buck regulator video, we get the average current as half of I1 plus I2. Let us now look at the inductor ripple current equation. Here, the dotted line represents average inductor current. When the switch is turned on, the inductor current increases from I1 to I2, and when the switch is turned off, the inductor current decreases from I2 to I1. Let delta I be the ripple current. It is split into delta I2 and delta I1. Delta I1 is a difference between average inductor current and inductor start current I1 during switch turn on. Delta I2 is the difference between inductor end current and average inductor current during switch turn off. Thus, we can write I1 and I2 as shown here. Now, knowing the values of I1 and I2 with respect to the ripple current values, we can substitute this in average inductor current equation. After substituting, we get inductor average current plus delta I2 plus inductor average current minus delta I1 divided by 2. After simplifying, we get inductor average current plus delta I2 minus delta I1 divided by 2. Here, average inductor current gets cancelled out and we get delta I2 minus delta I1 divided by 2 is equal to 0. Hence, we can write delta I2 is equal to delta I1. We know that delta I is split into delta I1 and delta I2. This means delta I is equal to delta I1 plus delta I2. Since delta I2 is equal to delta I1, we can write delta I is equal to 2 delta I1. On further simplification, we get delta I2 is equal to delta I1 equal to delta I by 2. This means inductor current swings symmetrically across average inductor current. With this, we can replace delta I2 and delta I1 with delta I by 2 in I1 and I2 to get this equation. Let us now look at inductor peak current ripple. From this waveform, it can be seen that inductor peak current is I2. However, we know the value of I2. Thus, inductor peak current is equal to inductor average current plus delta I by 2. From our previous videos, we saw that I in is equal to I out divided by 1 minus t. In steady state, the average value of inductor current is input current. Thus, I out is equal to V out divided by R load. Let us substitute output current in the input current equation. We get I in is equal to 1 by 1 minus t into V out divided by R load. We know that when the switch is turned on, inductor voltage is equal to the input voltage. The ripple current is given as V in dt divided by L. Considering d as a duty cycle, on time is given as dt. Let us substitute on time in our previous equation. We get inductor current di as V in t d divided by L. Now, we know the input current equation. We also know the ripple current equation. We can substitute these values in inductor peak current equation. After substitution, we get inductor peak current as shown here. To conclude, we can write inductor average current is equal to half of I1 plus I2. Inductor ripple current I1 is equal to inductor average current minus delta I by 2. Inductor ripple current I2 is equal to inductor average current plus delta I by 2. Inductor peak current is equal to 1 by 1 minus t into V out divided by R load plus V in t d divided by 2L. In this video, we saw inductor current equation of a boost converter in continuous conduction mode. We will learn more in our subsequent equations. Until then, let's keep exploring and learning. Thank you.